thought I'd get this going for you.
Thanks, Stuart.
Because I know this computer takes forever, so I'll just make it too dark for you to see. These computers are worse.
They are so slow, these computers now, aren't they? Thanks, Stuart. I appreciate that. Okay, we might make a start if that's okay. We've just discovered that in fact the display on the right-hand side, your right, my left, is much clearer than the display above the console, but the display above the console is the one that is recorded via echo. So I hope it's not distracting, but I think it's probably worthwhile if you don't mind having both. The one on the right is much clearer and certainly will show the colours better in the diagrams. The one on the left is being recorded, which is why I can't dull it or mute it. At least we have the lights working today, so that's a good thing. What we're going to do today, this afternoon, is to talk about gas carriage. And obviously the two gases with which we're particularly interested are oxygen and carbon dioxide. So what we're doing is trying to work sequentially through the whole process of respiration. So very quickly, as you know, we've spoken about the mechanics of breathing. That is, what do we do in order to get air into and out of our lungs so that gas exchange or respiration can occur. We then spoke about respiration and how that impacts on the partial pressures or concentrations of the gases, particularly concentrating on oxygen and carbon dioxide, for obvious reasons. We now need to look at how we transport them from the lungs or the alveoli, moving into the pulmonary capillaries around the body. In what form and what's its impact? And then tomorrow, we'll speak about the regulation, which is probably the key or the most important part of the whole lecture system. How do we control it? Well, why do we control it? Pretty straightforward. But more importantly, how do we control it? So that's what we're going to do, the transportation today. 3 points, very straightforward. The introductory points are meant to be straightforward. We will learn today in the lecture that we use the cardiovascular system, the blood, to transport oxygen and carbon dioxide between the lungs and the tissues and back to the lungs. And that makes perfect sense because, in fact, virtually every cell in the body receives blood flow. There are some notable exceptions, particularly the cornea of the eye. Obviously, you don't want blood vessels infiltrating the cornea because that will occlude light rays and hence your vision. So we have an adaptation that will be spoken about in other lectures to ensure that those cells are supplied with oxygen and can remove their carbon dioxide. But that notable exception aside, virtually every other cell in the body receives a vascular supply, and it's perfectly adapted to transportation of gases. Now, we transport the gases in a number of forms. Firstly, and in no particular order, not in order of importance, as we'll see, the gases can be dissolved in plasma. There's a problem with that, as I've already flagged, particularly with oxygen, because oxygen is not particularly soluble in liquid. Carbon dioxide is more soluble, but again, it's not totally soluble either. So that will work, but not work very well. Our backup plans are that we combine the gases to a substance called hemoglobin, which I'm sure most of you already know is found in red blood cells or erythrocytes. We'll talk about that. And in one particular instance, we convert that gas into something else. So if in fact that gas is not particularly soluble, let's convert it into something else which is much more soluble. And then we solve our dilemma. And we'll see how we do that and in what circumstances in a moment. We're going to speak about oxygen and carbon dioxide, so we'll start with oxygen because in some ways it's fairly straightforward in terms of how we transport it, but there's a big degree of complexity that we'll deal with in a moment. So, oxygen, about 1.5%, and again, we use about because there's no set absolute value, but approximately 1.5% of the oxygen that you and I have in our body at any time, in our blood, I should say, not in our body, in our blood at any one time, is physically dissolved in the liquid component of the blood called the plasma and the fluid of the red blood cell, the erythrocyte cytosol. And I've already said why that's only 1.5%, because oxygen not particularly soluble in fluid. So what do we do with the remaining 98.5% of the oxygen that you and I have in our blood? Well, it's chemically combined to that substance we mentioned earlier called hemoglobin. So, and again, there's an expectation that this is not unfamiliar to you, but certainly hemoglobin, often just known by its abbreviation of H, capital H, small b, hemoglobin binds to oxygen. And it binds specifically, so one molecule of hemoglobin binds to 4 molecules of oxygen. And it does so in a structure indicated in this diagram on the bottom right-hand side. And again, I apologise that it's unreferenced. I grabbed it from the web, forgot to indicate where it came from. But, so my bad, but nevertheless, here is a picture of hemoglobin, or a representation, I should say, of hemoglobin. It's a drawing of it. And you can see that one molecule of hemoglobin has 4 heme groups. Now, the heme group is the convoluted proteins that kind of look like, well, what do they look like? Elongated balloons. Can't think of anything more than that. So there's 4 of them, and they're indicated by the Greek letters 2 alphas and 2 betas. Now that's not particularly important to remember. There is some relevance that I'll get to in a minute. Now each of those heme groups, those globin molecules have a heme group. And the heme groups are represented by these green discs attached to the globin. Okay, so 4 globin chains. They're those sort of elongated sausage convoluted materials, and each of them has a heme group represented by the green disc. The relevance of that is that the oxygen binds to the heme groups. And because there's 4 of them, that explains why up to 4 oxygen molecules can bind to each hemoglobin molecule. When the hemoglobin molecule is fully saturated, that is, there is 4 oxygens bound to it, we call that molecule oxyhemoglobin, or that structure oxyhemoglobin. And notice that obviously that process is fully reversible. So, hemoglobin, in the presence of oxygen, and this would normally occur in the pulmonary capillaries, because that's where oxygen's diffusing into. So in the presence of that oxygen, hemoglobin forms oxyhemoglobin. and we say it's then fully saturated with oxygen. There's 4 oxygens bound to the 4 heme groups. But in areas of low oxygen, which you might find in working tissues, the reverse happens. The oxyhemoglobin dissociates into hemoglobin and free oxygen. And that free oxygen obviously is then available to be taken up by the tissue cells for their metabolic demands. You don't need enzymes, you don't need chemicals. This is a fully, simply reversible equation. Just before we leave that, and I said there was some relevance to the globin chains, the protein chains, in the adult, certainly there are 2 alpha and 2 betas. Now, spending 1 or 2 minutes only to indulge you is that in the fetus and the newborn, the globin chains are somewhat different. So in fact, you'll find in the fetus there are 2 alpha and 2 gamma chains. Now, what's the relevance of that? Why is that interesting? Well, the only interest is the gamma chains that you find in the fetus has a much stronger affinity, a much stronger attraction to oxygen. So you might think, well, a fetus lives in a very low oxygen environment. So how can a fetus carry the same proportional amounts of oxygen as an adult? Well, it does so by having this different globin, much stronger affinity to oxygen, so is able to bind oxygen in lower partial pressures or concentrations. Now, just prior to birth, that hemoglobin molecule is no longer produced, and the adult, the fetus, the late-term fetus, starts producing the so-called adult hemoglobin. And that process is fully complete by probably about 3 to 6 months of age. So just be aware that there is a fetal form of this hemoglobin which has some relevance for fetal development. That aside, let's look at hemoglobin. The other important thing about hemoglobin is that it allows us to carry far more oxygen in our blood than if it wasn't there. And that's really clearly demonstrated by this really good diagram, in my opinion, taken from Widmeyer. A similar type diagram is also found in Silverthorne figure 18.7. I think this is much more straightforward, which is why I'm choosing to show this one in the lecture. So let's deconstruct this and see why it's relevant. In the left-hand panel, we have 2 compartments, A and B. There are equal numbers of oxygen. The oxygen is represented by the yellow circles, the yellow dots, and the arrows indicated, like everything else, it's in movement. And because it's in movement, it applies a pressure, a partial pressure. Now, because there are equal numbers of oxygens in compartment A and B, and they're similarly mobile, we can say that the partial pressure of oxygen in solution A is the same as the partial pressure of oxygen in solution B. Simple as that. But if we add hemoglobin, represented by the large blue circles, to compartment B, and hemoglobin has an affinity, that is a strong attraction to oxygen, much of the oxygen will bind to the hemoglobin. Now, I did write a letter to Widmeyer, but they ignored me, and fair enough, I would ignore me as well, to say that in fact I love the diagram, thought the yellow was a stroke of genius to use as an oxygen colour, only joking, but what I didn't like is the fact that the hemoglobin's got 3 things bound to it and then's got about 5 or 6, so it's kind of weird when you've just in the text said there's only 4 oxygen molecules per hemoglobin, and now you're showing kind of random numbers. Okay, yeah, as I said, probably reported me to the relevant authorities and didn't reply, and it made me feel a little bit better, which was the point of the whole exercise. The relevance, other than me sharing my embarrassment with you, which I'm just realising as I turn bright red, is also that, in fact, don't be confused. It does not, don't think that I was lying when I said that there are 4 oxygen molecules to haemoglobin. This diagram is at fault. Moving on, we add our haemoglobin to compartment B. The oxygen binds to the haemoglobin, but it's only the free haemoglobin that contributes to the partial pressure. Obviously, if the oxygen's stuck to the haemoglobin, it can't impart a pressure. It's not moving. So it's only the free oxygen that is contributing to the partial pressure. So now, even though there are the same number of oxygen molecules in compartments A and B, we say that the partial pressure of compartment A greatly exceeds the partial pressure of compartment B. So, because the partial pressure in A is greater than B, what will oxygen do, provided this membrane is permeable? It will move from compartment A to compartment B until equilibrium is reached. So now the number of free molecules, and I'm talking about the right-hand panel if you're listening to this, the right-hand panel, we have 2 oxygen molecules free in compartment A, 2 free in compartment B, so the partial pressures are now equal, even though compartment B clearly has much more oxygen. So that's the other advantage of having haemoglobin. It allows us to carry far more oxygen in solution without it affecting the partial pressure, and this is obviously fortuitous or beneficial for you and I. Everyone happy enough with that? We spoke in the first slide by indicating that, in fact, the binding of oxygen to haemoglobin is fully reversible. And obviously it's going to form oxyhemoglobin in oxygen-rich areas of the body, such as the pulmonary capillaries, and it's going to dissociate in oxygen-poor regions, such as the fluid surrounding the tissue cells. But let's look at this in much more detail. And we come up with probably the key diagram in terms of transportation of gases around the body, which is Widmeyer figure 1326 or Silverthorne figure 18.9. They're the same diagram. That's good. Very quickly, the x-axis is the partial pressure of oxygen in its units of millimetres of mercury, ranging from 0 to 140. That's just an arbitrary range. And the y-axis is the percentage of haemoglobin saturation. Now, be aware that, and that range is obviously from 0 to 100%. You can't get more than 100%. Now, just be aware that if we're looking at 50% haemoglobin saturation, we've got 2 choices, basically. Does that mean that all the haemoglobin only has 2 instead of 4 oxygens bound to it, which is 50% saturated? Or does it mean half the haemoglobin is fully saturated and the other half is totally unsaturated with oxygen? So it's again 50%. It is the latter. So this haemoglobin saturation basically tells us how much of our haemoglobin is fully saturated. And that's relevant because a haemoglobin will give up all its oxygen before the next haemoglobin will give up its oxygen. Okay? So once the haemoglobin starts giving up some of its oxygen, it weakens the affinity, and so it'll give up all its oxygen. And that becomes important in a moment. Okay, 2 key areas of partial pressures indicated in this diagram correctly. Systemic arterial PO2 of 100, because as we learnt last week, in pulmonary capillaries and systemic arterial blood, so-called fresh blood, don't like the term, it's okay, the partial pressure of oxygen will be about 100. And in systemic venous blood and pulmonary arterial blood, going back to the lungs, the PO2 will be likely to be much less, in the order of about 40 millimetres of mercury. So they're our key reference points. Let's look at what happens at a PO2 of 100. Well, at a PO2 of 100, no surprise, almost 100% of our haemoglobin is fully saturated. It's around about 98, 99%. And that's perfectly adapted. That is why we are adapted and we try and achieve a PO2 of 100 in our blood, because that's obviously going to virtually fully saturate our haemoglobin. It also tells you, is there an advantage of having a PO2 in your blood more than 100? Kind of not at all, because you're not going to be able to transport any more oxygen bound to haemoglobin at higher PO2s, because it's virtually fully saturated at a PO2 of 100. So there really is virtually no benefit of having a higher PO2 than 100. Now you might say, and I'm digressing, but you might say, well, what about those hyperbaric chambers where people who have very poor healing of tissues? You might have heard of people who go into the hyperbaric chambers and breathe in rich amounts of oxygen. What's the benefit of that? Well, the key is that they are in higher pressure. So what happens in higher pressure and pure oxygen, you force more oxygen into solution. And so there's more physically dissolved in your plasma, and that can reach the poorly vascularised tissues like tendons and ligaments, and it might accelerate healing. So there is some benefit under those circumstances. But we can't change the pressure of the environment sort of consciously, so it's not relevant to us. I was travelling in Japan recently, and there was lots of those, there was enough of these little oxygen booths. I can't remember what they call them. They sort of, you go along to this booth and there's a couple of seats there, and it's all, bright colours, and the solutions that you then, put these gas things up your nose, and you sort of breathe in oxygen from these very brightly coloured bubble solutions. And the whole idea is it's meant to be therapeutic. It's meant to improve your health and well-being by breathing in rich oxygen. Well, you and I know at normal atmospheric pressure, we can speculate that there's no benefit whatsoever. Okay, it might make you feel good by spending 30 or 40 bucks by breathing in oxygen going through a pretty coloured drink, but, and your choice, but I would suggest save your money. It's not going to work. It doesn't work. Other than that, PO2 of 100, 100%, virtually about 98% of our haemoglobin is fully saturated. Now, PO2 starts to drop. So what would happen if you had your breathing compromised a little bit? So you weren't breathing normally, or you're in an environment where there wasn't as much oxygen in the atmosphere as it would normally be, and say your PO2 drops in your arterial blood from 100 to 90 to 80. Now that might be a 20% drop in the PO2. How's that going to affect you? Well, if we look at our haemoglobin saturation, because of the shape of the relationship, it's not linear, it's sigmoidal, shaped like an S, that in fact you can drop your PO2 quite significantly and your haemoglobin will still be virtually fully saturated. And that's an adaptation. That's very useful for you and me, because we can drop our PO2s by, to 90, 80, 70 without suffering any significant reduction in our saturation of haemoglobin. So you and I won't even know that the PO2 in our blood has dropped from 100 to 90, 80, 70, even 60. So that's the functional relevance of having a flattened region in the top part of our haemoglobin oxygen dissociation curve. Let's look at the other side of the equation in our tissues. PO2 of 40. So in the tissues, when your PO2 is 40, how much of your haemoglobin is fully saturated? Slightly less than 80%. So slightly more than 20% of your haemoglobin has given up all its oxygen. Now that's important because it means we've got quite a lot of oxygen in reserve, still attached to our haemoglobin. So when somebody says to you, venous blood contains no oxygen, that's totally untrue. There's still quite a lot of oxygen bound to haemoglobin in venous blood, which we've got in reserve. Say if your PO2 in your tissues dropped from 40 to 30 because you're exercising, now that's only a relatively small drop in PO2 of 10 millimetres of mercury, what happens to the saturation of oxygen? Well, instead of being about 80% saturated, a drop of PO2 of about 10 will probably means that your haemoglobin will be about 55% saturated. So you have delivered an additional 20% of your haemoglobin's oxygen to your tissues. Okay, so you've virtually doubled the oxygen delivery to your tissues with a small drop of PO2 in those cells. And that's very advantageous. So the steepness of the relationship in low PO2s mean that a small drop in PO2 in your tissues delivers a large amount of oxygen. Is that clear? Because if your haemoglobin is not fully saturated, obviously the oxygen's been released and that is available for your working cells. So they're the two important components of this relationship. The flat part at high PO2s is protective because it means you can drop your PO2 by a fair bit without suffering any reduction in haemoglobin saturation. The flip side in the tissues, a small change in PO2 will lead to a big drop in haemoglobin saturation, which means a lot of that oxygen is then being released and delivered to the working tissues, which is exactly what you want. So that explains the physiological relevance of the sigmoidal relationship in oxygen-haemoglobin dissociation. Is everyone happy enough with that? The last thing, we're speaking about percentages of haemoglobin saturation, but if you're like me, that kind of doesn't mean too much. So I'm going to show another diagram which has only one more axis from the previous one, and that is the what do you call the second y-axis? Y-axis number 2. It might be Z. It might be, I don't know. Okay, so it's the second y-axis on the right-hand side, which has the mils of oxygen per 100 mils of blood. So it says how much oxygen is in your blood. So that's the only difference to this diagram. So the only thing that I'm interested in looking at is as your blood travels from the lungs with a PO2 of 100 to the tissues with a PO2 of 40, we've already worked out that the haemoglobin saturation drops by about slightly over 20%. What's that in real terms? How much oxygen does that release or deliver? Well, this tells us it delivers about 5 mils or unloads about 5 mils of oxygen for every 100 mils of blood. How much blood do you and I have typically in our body? If you're a big person, 6 litres. More typically it might be about 5, but 6 is okay. 5 is much more typical of an average individual. So if you've got 5 litres of blood and your haemoglobin unloads 5 mils of oxygen for every 100 mils, how much per minute, how much oxygen do you deliver to your tissues? 50 times 5, 250 mils. So every time your blood travels around the body, does a circuit of the body, that is from lungs back to the lungs, you have delivered 250 mils of oxygen to your tissues. Now, how many times does it do a circuit around the body? How long does it take for your blood to do a circuit in your body? What's cardiac output? Remember from semester 1 or year 1. Typical cardiac output of a typical individual? 5 litres per minute. So if you've got 5 litres of blood in you, how long does it take for your blood to do a circuit of your body? 1 minute. So now we've got our full story. You deliver 250 mils of oxygen to your tissues every minute. and that is what happens. And so I've got a few sentences which summarise the main points that we went through in those diagrams. So there's nothing new here. I've just given you a summary to help along the way. Before we leave oxygen, obviously this situation is what normally happens, but it's not absolutely fixed at all times. There are some things that you and I can do to change this oxygen-hemoglobin saturation relationship. And it's no surprise that there are a few key things that can affect the unloading of oxygen to hemoglobin. So change the affinity or the binding of oxygen to hemoglobin. Now, when might you want to deliver, under what circumstances might you want to deliver more oxygen to your tissues? When your tissues are working. So it's of no surprise whatsoever that a couple of those, well, all these conditions occur as a consequence of you working. And they are, and I've taken this from Widmeyer, or you can see Silverthorne, they are, I'll go from the bottom upwards, the pH, acidity. So as we'll learn in a moment, when you exercise, you produce carbon dioxide. Carbon dioxide reacts, as we'll see in the very next slide, to produce acid. So when your tissues are working, you will produce more acid and the pH will drop of the blood. And that shifts the curve to the right. So instead of being the yellow line, which is a relationship we just discussed in our previous two overheads, when you are working and the pH drops, the curve or relationship shifts to the right, which means that at the same PO2, less hemoglobin is fully saturated, which means more oxygen has been delivered to the tissues, moving the curve to the right. The other thing that can change the oxygen-hemoglobin dissociation curve and shift it to the right is temperature. So when you're working, what happens to your body temperature? It increases. So it's no surprise that body temperature will also shift the curve to the right, thus releasing or delivering more oxygen to your working tissues. And finally, there is a chemical that red blood cells have. And it's released by red blood cells when you have low levels of oxygen. And that chemical also shifts the curve to the right. So when your red blood cells don't have enough oxygen, they release this chemical, shifts the curve to the right, and more oxygen will be unloaded, which is what you want. Now that chemical is called DPG, or in some textbooks, Silverthorne being one of them, it's called BPG. So maybe in brackets after the DPG, put BPG. It's the same chemical. Now, I don't care that you know what it's called, but it happens to be called 2,3-diphosphoglycerate or 2,3-biphosphoglycerate. Bi and di mean the same thing too, so that's why the names are interchangeable. So, take-home message of this overhead. Under certain conditions, unsurprisingly those conditions that you find when you are working, you can shift the curve to the right, and hence you will unload more oxygen at the same PO2s to your tissues. They being pH, or acid, temperature, and the release of this special chemical. Works very nicely in you and me. Let's look at carbon dioxide. Now, I've put this, I'm going to talk about acids and bases a little bit. I assume that everybody has some basic knowledge, no pun intended, of acid and bases. I'm not going to waste 5 minutes of your time in the lecture, but I have put some notes up for you to think about. As I've said, this is for review only. I'm not going to cover it in the lecture because it's not worth your time. So let's look at carbon dioxide. If you do not understand something about acid and bases, have a quick read of those lecture notes or ask somebody and you will have the information you need. So let's look at carbon dioxide. In many ways, a bit more straightforward. How do we transport carbon dioxide in the body? Now remember, where do you and I get our carbon dioxide from? Certainly not the atmosphere, because there's virtually none in the atmosphere. So virtually all the carbon dioxide in your blood comes from your working tissues. You generate it. Okay. Now, when your tissues generate carbon dioxide, about 7% is dissolved in plasma. Much more soluble than oxygen, but still not totally soluble. So we've still got to do something with the 93%. 23% is bound to hemoglobin. And when the hemoglobin combines with carbon dioxide, we call it carbaminohemoglobin. Now, is it competing with oxygen? No. Oxygen, as we established, binds to the heme groups of hemoglobin. Carbon dioxide tends to bind to the globin chains of the hemoglobin. So it's not in direct competition with oxygen. Having said that, an oxygen that has given up, a hemoglobin that has given up its oxygen will have a much stronger affinity to carbon dioxide than one that is still fully saturated with oxygen. And that makes sense. So a hemoglobin that has given up its oxygen will have a much stronger attraction or affinity to carbon dioxide than one that's still fully saturated with oxygen. But they're not in competition because they bind to different regions. But that's only 23%. Because hemoglobin doesn't have the same affinity to carbon dioxide as it does to oxygen. So what do we do to the remaining 70%? Well, if only 7% of CO2 is able to be dissolved in plasma, why don't we convert the CO to something that is almost instantly soluble in plasma? And what we convert the carbon dioxide into is bicarbonate. And that's fully soluble. How do we convert carbon dioxide into bicarbonate? Very straightforward. In red blood cells. Now, why do I say in red blood cells? Because unlike oxygen binding to hemoglobin that didn't require any enzymes, to convert carbon dioxide to bicarb, you do need an enzyme. And that enzyme is called carbonic anhydrase. Generally, anything with an ASE will be an enzyme. And that enzyme is in very high concentrations in red blood cells, which is why this occurs in red blood cells and not in other parts of the body. So, carbon dioxide enters red blood cells. It combines with water. Well, there's plenty of water everywhere, particularly in red blood cells. And in the presence of this enzyme forms carbonic acid, H2CO3. Carbonic acid is very unstable. So almost instantly, carbonic acid dissociates, doesn't need an enzyme because it's unstable. It will immediately dissociate into free hydrogen ions and bicarbonate ions. And that bicarb is much more soluble than the free CO2 was, so it dissolves and is then moved into your plasma, which is how you transport it around the body. Is that fairly straightforward? Nothing is as simple as it seems in the human body. It isn't too much of a difficulty, but there is another complexity that we need to deal with. So let's look at this in a schematic form, only because to me it makes more sense looking at a picture. And I've taken this from the web, but a diagram similar to this can be found in Widmeyer or Silverthorne as referenced. So here we have our carbon dioxide produced from your tissues. It enters the blood. As we just discussed, 7% will dissolve in the plasma, That's fine. The remaining 93% will diffuse into the red blood cells down the concentration gradient, where 23% will bind with haemoglobin to form carbaminohaemoglobin. Only 23% because carbon dioxide does not have the same affinity to haemoglobin that oxygen does. And it'll bind to the globin chains, not the heme groups. So it's not going to kick off any oxygen. The remaining 70% will be converted to carbonic acid because red blood cells are rich in the enzyme carbonic anhydrase. This carbonic acid is very unstable, so it almost immediately dissociates into hydrogen ions and bicarb. The bicarb then moves into the plasma in order to be transported around the body, particularly back to the lungs. You might have already seen one problem, and I can identify another as well. What's the problem with this? Well, if you're dissociating carbonic acid into bicarb and free hydrogen ions, what are free hydrogen ions? Acid. So if you're producing a lot of hydrogen ions, you don't want the pH of your red blood cells to plummet, to become very acidic, because that will damage the delicate structures. So we've got to do something to these hydrogen ions because they're pure acid. And what we do is we recruit our old friend haemoglobin. It binds to the hydrogen ions and buffers it. Now, don't get too worried about the term buffer. If you've done chemistry, I'm sure you won't be bothered. Even if you haven't done chemistry, buffering just means you take it out of the pH equation. So it binds to haemoglobin, it no longer contributes to pH, so you don't get any acidity as a consequence. So haemoglobin, really important for three things: oxygen, CO2 and hydrogen. The other problem that you may not have identified, obviously, is that if you pump out bicarb into the plasma, what did you learn in semester 1 or year 1? If you remove negatives from a cell, what does that cell consequently become? If you're removing negative charges from the inside of the cell, that cell will become positive, depolarized. And changing the polarity of a cell will change its function. So we want the bicarb into the plasma because that's how you're transporting it around the body, but you don't want to massively depolarize your red blood cells. So what do? Or what do we do? We simply exchange or swap the bicarb with another negative charge. And that happens to be chloride. Chloride in high concentrations in the plasma. So for each bicarb you pump out of the red blood cell, you pump a Cl into the red blood cell. So the polarity or the polarization of the red blood cell does not change. And that's called, obviously, the chloride bicarb exchange or the chloride shift. So we identified two problems, but we also found how the body resolves those two problems. And that's carbon dioxide. And here's some notes about CO2. Nothing new here except for point 3, because I always forget to say it. If we looked at or we calculated how much oxygen we transport and deliver to our cells every minute, and we worked that out to be 250 mils, we need to then know, we can't really work it out, but we need to know how much carbon dioxide we produce in our cells every minute. And point 3 tells us that under normal conditions, and by normal conditions I'm probably meaning under normal dietary conditions, we produce about 200 mils of carbon dioxide each minute, which is slightly less than the amount of oxygen we consume. As I said, it depends on your diet. If you're studying dietetics or nutrition, you probably know that a diet that's very rich in carbohydrate, you might get a closer to 1-to-1 exchange from oxygen to CO2. But if you have a very high fat diet, it drops to about 1 to 0.6. So you get about 60% of your CO2 produced compared to the 100% for every 100% of oxygen. But in a normal mixed diet, it's approximately about 80%. 250 mils of oxygen we consume per minute, and we produce about 200 mils of carbon dioxide every minute as well. Okay. And that's quite a significant amount, because if we don't get rid of that CO2, it can kill you quite rapidly. Now, I saved the best to last, and I know this can be quite a difficult diagram to look at because there's a lot going on, but I thought it was a good thing just to summarise what we've learnt in today's lecture. And I'll take literally 2 minutes to do so. There's nothing new here, I'm just putting it all together. So I thought this was useful for you to see it in context. The top panel looks at what's happening to oxygen. The bottom panel tells you what's happening to CO2, carbon dioxide. The left-hand side, as you can see, is what's happening in the pulmonary capillaries as they pass the alveoli. And the right-hand side is what's happening in the tissue capillaries, the systemic capillaries, as they pass the working cells. Let's look at oxygen, because it's fairly straightforward. High levels of oxygen in the alveoli, lower levels of oxygen in the pulmonary capillaries, as we learnt last week. This will drive oxygen into the blood, down its partial pressure gradients. That oxygen, what happens to it? 1.5% is physically dissolved in the plasma. 98.5% of the oxygen moves into the red blood cells, and it does so because it has a very strong affinity or attraction to haemoglobin, and it forms oxyhemoglobin. It gets to the tissues or any region which has less oxygen. Because the level of oxygen in the tissues is lower than the blood, the free oxygen, which is in the plasma, moves out of the blood into the tissues. This stimulates the dissociation of oxygen from haemoglobin, just means it breaks off the haemoglobin, and then the oxygen is released, moves into the plasma, and then ultimately moves into the tissues. Every minute, 250 mils of this is occurring in our bodies collectively. What's happening to CO2? CO2 is derived not from the alveoli but from your tissues. So the CO2 produced by your cells, because there's more CO2 in your cells than your systemic capillaries, CO2 moves down its partial pressure gradient into the blood. 7% dissolved, 93% moves into the cells. 23% binds to haemoglobin to form carbaminohemoglobin, particularly the haemoglobin that's given up its oxygen, which is just done at the same time. So it's perfectly related. It binds to the globin. The remaining 70% of the oxygen forms carbonic acid because of the presence of the enzyme carbonic anhydrase. That immediately dissociates, because it's unstable, into hydrogen ions, which is buffered by haemoglobin, so you don't acidify your blood cells and kill them. Well, you don't really kill them, but destroy them. And the bicarb is pumped out into the plasma in exchange for chloride, so that the polarity stays neutral. And then when it gets to the lungs, which has low levels of CO2, the reverse happens. CO2 moves from the plasma into the alveoli, thus triggering the reverse of the same set equations that we saw in the tissues. And 200 mils of CO2 in normal dietary circumstances is being removed from the body every minute. I hope that gives you an understanding of what's happening in the body with gas exchange. Thanks again for your attention. I'll see you tomorrow when we look at the control, which is, after all,